So the third assignment in this unit on conic sections is going to be about ellipse and ellipse. So we're going to learn all about ellipses. We've already talked about parabolas and circles. And so let's start talking about the definition of an ellipse. It's kind of an interesting one. An ellipse is the set of points in a plane such that the sum of the distance from two fixed points is constant. So those two fixed points are called the foci, and the constant we're just going to call a k value. So here's an example of what we're talking about. Here we have two fixed points, two foci, and here's an ellipse that goes around those two foci. And the definition says this, that if I were to take a walk from this foci and actually hit the ellipse and then walk to the other foci, that distance is the same no matter where I go on the ellipse. So I can go there and those two distances would be the same. I can go right here, and that distance is the same as that distance if I add those two distances together. I can even go down here, and this distance is also the same. One of the interesting things about this then is this. You can imagine a race where this is the starting line, and this is the finish line. You could have a race where the race would be to start at the starting line, go touch the ellipse anywhere on the ellipse, and then go to the finish line. And it would be a fair race, because everybody will be running the exact same distance. Okay, so you might have one person that runs like this and another person that runs like this, but those two distances would be identical. And that's what the definition of an ellipse is. Interesting characteristic about an ellipse is this, that these two angles are always going to be the same. One's called the angle of incidence and the other is the angle of inclination. And so, because those distances are the same, if you were in a room, the Capitol building in Washington, D.C. is an example of this. There's a story of a president, and I don't know which president it was, but he was sitting at his desk. There were foreign diplomats that he put at a table over here. They would discuss something and then come over across the room and present it to the president. Well, he could hear their entire conversation because their voice, their sound waves would bounce off against the walls of the Capitol building and then reflect and go directly into the president's ear, like they were just talking, as if they were talking right next door to him. One of my ideal arrangements for a classroom would be to teach in an elliptical classroom, because I could teach at one focal point, and I would have students sitting anywhere around the room, but I would put that one student that just doesn't pay attention at the other focal point. And then I could stand at this focal point and whisper. My sound waves would all reflect off the wall and come back and hit him all at the same time. So I could whisper something that nobody else would hear, but he could hear it like I was whispering it in his ear. So I would love to be able to teach in an elliptical classroom where that person could hear everything I had to say, specifically to him, like, hey, you better pay attention. Okay? Let's talk more about what's going on with this particular shape. We have a major axis that goes along the, in this case it would be the x-axis, because it's called the major axis because it's the longer of the two axes. The other axis is called the minor axis. It's the shorter one. The major axis contains the two focal points. So we have the focal points that are along the major axis. It's possible to have an ellipse that is a long skinny ellipse instead of a short fat one. And then the major axis would be along the y-axis, and the minor axis would be along the x-axis. Not only that, we have vertices. On the major axis, there's two vertices on the major axis, and then there's vertices along the minor axis, but those are called the co-vertices. So if we were in a tall, skinny ellipse, this would be a vertex, and so would this, and then on the right and the left would be the co-vertices. We also are going to be talking about an A value. An A value is the distance from the center of the ellipse to one of the vertices. So the A value is horizontal in this particular ellipse, but it would be the vertical one here because it would be the bigger one. And then the B value is the distance from the center of the ellipse to one of the co-vertices along the minor axis. So we have an A value, a B value, along the major and minor axis that lead to the vertices or co-vertices. Let's take a look at what the equations would look like. And there's two different forms depending on what the ellipse looks like. If the ellipse is a short, fat one like the one that we have here, then the equation is going to look like this. We're going to have the x squared over the a squared okay, because the A is along the x-axis, and the y squared over the b squared because the y is along, or the minor axis is along the y-axis, and that equals 1. And then if it's switched around, if it's the shorter and, or the taller and skinnier ellipse, then this would be the A value here, and this would be the B value, and it would be the x squared over b squared, and then y squared over this distance, which is the A squared, equals 1. And an interesting thing here is that if the two focal points were squeezed together, we would actually have a circle. Okay, and the ellipse is going to look more and more like a circle the closer and closer those vertices get to each other. And a circle is really a special kind of an ellipse where the two focal points are the exact same thing. So we'll talk more about that later on in this video. Let's just take a look at how an equation is developed. So I'm going to start with one of the covertices at the point 3, 0. Which means another covertex is going to be at negative 3, 0. Then we have a vertex at 0, negative 6, which is down here, which means another vertex is going to be at 0, positive 6, which is up here, which means we have an ellipse that looks something like this. So this particular equation is going to look like this. We're going to have the x squared over, this is now my b value, which is 3, 3 squared is 9. So x squared over 9, plus my y squared, over, in this case, it's the A value, which is 6. That's 36. If I square it, that equals 1. And that's my equation for this ellipse. Okay, so let's go ahead and, let me just pause this. So let's go ahead and go on to another example. Let's say we have an ellipse that is 10 units wide. So I'm going to go, if this is the center, then I would go 5 units to the right, 1, 2, 3, 4, 5. There would be one covertex or vertex, and 1, 2, 3, 4, 5 to the left is my other one. So that's 10 units wide, and it's 8 units high. So I'm going to go from positive 4 to negative 4, which is right here. So now my ellipse looks something like this. And my equation is going to be x squared over this distance, which is 5 squared, which is 25, plus y squared over the b value here, which is 4, that's 16, equals 1. And that's going to be our equation. So I'm going to stop this video and create another video that you can watch for the second half of what you need to know about ellipses. So we'll pick this up in video number 2.